Okay, that stage coloration change. Looks like it's time for me to get started. So welcome to the last session of SQLDay. Hopefully you've had a great event, and we're going to close things out on a high note. First, very briefly, thank you to everybody who helped make this event possible. I appreciate all the work that the organizers have put into it, the sponsors who are on the screen behind me, everybody who's really put a lot of effort into making this hopefully a very successful event for you. So now, let's get started talking about anomaly detection. My name is Kevin Feasel. I'm a Microsoft Data Platform MVP. I live in Durham, North Carolina, and I run a predictive analytics team. I also have a blog called Curated SQL, where I like to find and link to 5 to 10 interesting posts per day on topics all across the data platform space. So that's curatedSQL.com. If you have questions throughout this, please feel free to raise your hand. I'm happy to take questions at pretty much any time. Or if you'd like to put them into chat, you're welcome to do so as well, and I can respond to them immediately. So what I want to do in this talk is explain what anomalies are, and then look at some techniques for detecting them. We'll build a couple of anomaly detectors depending on time. We'll definitely get to one in .NET, and then I hopefully will be able to show you the Azure Cognitive Services anomaly detector, though that might be something that I leave as an exercise for you afterward. So let's jump into a discussion of what anomalies really mean. At its core, an anomaly is an outlier. It's different from the norm in a way that merits interest. So there are two preconditions. It must be different and it must be interesting. But there are quite a few conceptual definitions of what an anomaly is, and I'd like to take you through some of them. We'll start with some general concepts, and then we'll go to technical definitions after that. The non-technical definition of anomaly is simply that we know it when we see it. I don't need to point out which bottle here is anomalous, which one's the weird one, because human brains are mapped, they're wired to understand differences, to recognize patterns, and to recognize differences from patterns. And there's a great evolutionary reasoning behind it, but essentially, we are excellent pattern matchers, or at least above average pattern matchers. So if you want to formalize this a little bit, I recommend learning about the Gestalt School, if you're not familiar with them already. This is a school of psychology which is dedicated to understanding how the brain works, and kind of came up with this notion that your brain is an abstract pattern matching device. In other words, we receive signals from our eyes, and the brain takes those signals and maps them to patterns it already has, and then that's what we see. So what this ends up doing is that there can be information that your eyes send to the brain, but that the brain ignores because it doesn't fit the pattern. And this is especially true as you spend a lot of time focusing on something, that you will tend to miss things that you didn't necessarily look for. That said, there are some principles here that we can understand and kind of guide us in our understanding of why general pattern matching can work as a way of detecting anomalies. So the first thing I want to talk about is the law of closure, where we fill in gaps automatically. So the brain here sees I have a square, a circle, and a triangle, despite the fact that each one of those shapes has gaps in it. We can then talk about the law of common region, where it is interesting to us if something is within a zone or outside of a zone. So despite the fact that these are all the same blue dot that I copied and pasted, some of them are going to be considered as part of one group, and others will be part of a different group because I put a gray box around them. So we're really good at noticing this is inside, this is outside. We can also pick out generally the foregrounds of images better than the backgrounds. There are some interesting exceptions. So this is a piece of art called Rubens' Vase, and on one side it looks like a pair of faces. On the other side it looks like a vase, but it's actually the same image. And I also palette swapped these so that we have what's white is black, what's black is white, because quite often people will see on one side one thing, on the other side the other thing. And if you kind of look at it from a little distance, especially because I have a white background, you'll see the vase on the left, the people on the right. But if I change the background just a little bit, you may see the people on the left, the vase on the right. Things which are nearer to each other are generally considered part of the same grouping. And if there's what we would consider abnormal separation, that will create a new group in our minds. So in this case, I take those dots, and because some of them are close to each other, we tend to think of them as part of a group versus dots that are separated. So it kind of looks like I have 4 groups of dots here. And we'll come back to the law of proximity a couple of times. I'm laying these out as foundational. As far as similarity goes, we group things together based on attributes like color, shape, and size. So you may be looking at this and seeing the blue dots, the gray dots, the yellow dots, and figuring, well, what do the yellow dots have in common? We do this automatically because they share the same color and everything else is of a different color. So we're able to intuitively group them as part of the same thing. One interesting thing about the way the mind works is that we want to follow a smooth path. So if I show you this image, the fact that we have the orange line and the blue line, and they break off so sharply, is a little disconcerting to our minds. What we would prefer to see, if this was black and white, if all the dots were the same color, then we would naturally see a straight line going across the horizontal and then a curved line around it. That's just how we would interpret the image. But here, because I've added the difference of color, we now interpret it as 2 different sets. And we have 2 sharp curves. So that actually goes a little bit against how our brain wants to work. We also perceive ambiguous shapes as simply as possible. So this is the law of symmetry and order. On the left, I have a single color, but your brain has already probably picked it up as square, circle, triangle, even if you don't look at the right-hand side, which is where I've changed the colors on them. We try to break things down so that we can see that, oh, this complex clump of things here is actually a lion sitting in the savannah, and we want to get away from that as fast as possible. So how does this work? How does this work for us, especially when we're not in the savannah getting chased by lions? Well, because we are pattern matchers, and we do try to apply fairly simple heuristics to visual inputs, we can see things that are not there, and you can take advantage of that as a learning experience, and you can also take advantage of it with optical illusions. Most optical illusions are going to be based off of the fact that we follow these sets of rules. But what I want to show you is this chart here on the right-hand side. This is just some National Football League statistics, 1 week of data, and this was passing yards versus points scored. And if you look at the chart, you can intuitively see that there is a line, that there is a relationship. It seems to be a positive relationship between passing yards and points scored, but that there are 2 dots at the bottom. So they seem like outliers. So we have taken advantage of some of the pattern matching skills we have to say, those look like a couple of outliers. If I were to draw a best fit line, here is what the best fit line looks like. It may not be the same line that you would intuitively draw, because you may be taking into consideration, oh, well, these two values down here seem weird. I wonder if the line is really up higher so that it's nice and comfortably fitting between all of the non-weird values. As far as a statistical function goes, though, this is the best fit line. And you can see how just a couple of values can drag that line down considerably. So that's our layman's conception of what is an anomaly. But it's quite ambiguous, and I left it ambiguous on purpose because there are some things which may look strange to you, but in fact are not anomalous. And at the same time, there are some things that may look reasonable, but technically can be anomalous. So let's separate that general concept and understand the more technical definitions. So the first technical definition I want to talk about is anomalies on a fitted distribution. So here I have a normal distribution, or at least mostly a normal distribution. And it follows a specific pattern. Its mean here is 0. Its standard deviation is 1. So it is the true normal. But then what I did was I took a few of the values on there and I made them extremely low. So there's a little bit of a hump on the left side where that arrow is. That leads us to the idea of how far away do we need to be from the general curve to be anomalous, to be weird. And we'll get into that in some detail in a little bit as we talk standard deviations. But I want to prime your mind for that first. Here is a box plot. This is, in this case, this is a number of invoices by month and by year. And the box plot is really great for us because it tells us several pieces of useful information. In the middle, that black line on the right-hand side where it says median, that is the 50th percentile. That's the midpoint in all of your values. Then you look for the 75th and 25th percentiles. So in other words, the box contains half of your values. Now, that box looks pretty big. That's because our values are kind of spread out, it looks like. But what you want to do then is take the interquartile range, which is the size of that box, multiply it by 1.5 in each direction, and find the highest point at the top and the lowest point at the bottom, which are within that range. And those are your whiskers. Those are the lines. So I have arrows pointing to the top and the bottom lines. Any value which is outside of those lines is called an outlier. So this is one technical definition of an outlier. It is more than 1.5 times the interquartile range distance from the median. And we can use that as a definition. It's not the only one. It may not be the best one, but it is one definition. Here's another example. This is called a process control chart. And you will find process control charts quite often in manufacturing and industrial uses. The idea here is that this tells us when a process is working within normal parameters, and we call that in control. So the gray box, hopefully you're able to see the gray box on here, but the idea here is that gray box represents you are in control. The process is working fine. So for example, if it is a drill press, it's drilling holes that are the correct diameter and within a certain tolerance. So you're staying within that tolerance. Maybe the line represents exactly the exact amounts and you're kind of bouncing around, but everything's okay. Then suddenly the holes get a bit larger than what they are allowed to be, representing those red dots. And now the process has gone out of control. So we can learn from there that yes, you're out of control. You have gone beyond allowable tolerance, and that way a trained operator may be able to understand what's happening, stop the machinery, fix the problem, and bring you back into control. So this information here, the outlier is the fact that you are outside of an allowable tolerance. When we're building out data sets, there are a couple of considerations I'd like us to keep in mind. And the first one is that we want data sets with certain specific properties. Ideally, we have one numeric feature that we want to measure. We should also have quite a few data points. My recommendation is minimum 30, preferable 60 to 90, and also include at least one full cycle of behavior. So what I mean by a cycle of behavior is that if you have seasonality in your data, that you have at least one full round of that seasonality. So for example, if I sell beach umbrellas, I'm going to sell a lot of beach umbrellas in late spring and into the summer. I will not sell many beach umbrellas in the middle of winter. If I only look at 1 month or 2 months of beach umbrella sales, I won't get the whole story. And I may consider something anomalous when really it's just that's normal, it's just in a different season. So I want to have enough historical data that I see the seasonality and that I can understand it. And in this example, this was the trend of using specific terms in Google searches. And we can see there is a distinct seasonal effect that each year people start entering the word spring, or in German, Frühling. Do we need time series data, though? Well, the short answer is no, we don't need time series data. In fact, we have an example that I showed you where we didn't have time series data, and that example was this football chart. So in this case, all of the data came from one time period, 1 week in time, and that was still good enough for us to collect that data and detect anomalies. So in this case, we made the assumption that all members, all the data points in here, follow effectively the same operational function. And what I mean by that is that they all follow the same standard behavior. If I have data points that maybe are significantly lower, but that's because I'm checking a completely different thing, then I can mess up my analysis. As an example, using American football, the game has changed considerably over the past 50, 60 years. And if I compared scores and values from 1970 to 1990 to today, that was 3 completely different time frames, 3 completely different eras. If you think of it in soccer terms, you have 1930s style soccer, park the bus style, and quite different from today's gegenpress heavy or attack heavy techniques. So you'll see scoring radically change between those eras. You'll see certain concepts, certain techniques radically change. And therefore, you don't want to necessarily compare A versus B because they're actually quite different. So let's talk tracking anomalies. There are quite a few detection techniques available to us, but there are some commonalities. And one of the first commonalities is we assume that points that are clustered near to each other are less likely to be anomalous. That's the law of proximity. If we have a lot of values that are pretty close to each other, we assume that that is the norm. And that also tells us that, well, for anomalies, they tend to be relatively few in nature. If you have a huge number of anomalies, it's not an anomaly, it's normal. So because there tend to be relatively few outliers, we can isolate those and perform techniques, processing techniques that may be relatively expensive per point, but end up being okay because there are so few of them. With time series data, we can also generally work from the assumption that changes from one point to the next are not drastic, and there is some predictability. If you're driving a vehicle, so you're driving a car and you are accelerating, the velocity at which you're driving the car, the speed will not drastically change from 1 second to the next. You may have the pedal down fully and accelerating as much as possible, and it may go up considerably, but it will tend to be a fairly smooth increase. You don't jump from 0 to 100 kilometers per hour and then drop down to 20 and then back up to 150. That's not how any of this works. So when we have time series, we tend to expect some level of smoothness. And if we see massive discontinuities, that can be a problem. And we also mentioned trend and seasonality. So we mentioned seasonality specifically. Trend is where things may get hot. Things may change fundamentally. So I may have a product that a lot of celebrities begin to endorse. And now that product has become much more likely to sell. And I can see that effect. So if we have some sort of event, some confounding event which affects the underlying distribution, what we may see as an anomaly may just be a change in the trend. Come back and talk about standard deviations a little bit. The standard deviation is a calculation of variance. How widespread, how spread out are things? And here's a quick sample. We have standard deviation of job satisfaction ratings for 3 groups. And I have 3 different charts. One of them in green has a standard deviation of 20 points. In red, it's 10. In blue, it's 5. And you can see that as the standard deviation shrinks, the density of this curve narrows as well. So, for example, if your standard deviation is 5, and you follow a normal curve, 1 standard deviation plus and minus will give you about 68% of your data. 2 standard deviations, 95. 3 standard deviations, 99.7. So in other words, between 35 and 65, you'll see 99.7% of the blue data. But the red data has a standard deviation of 10. So now we're talking about 20 to 80. And the green standard deviation has 20. So basically, any value from 0 to 100 is acceptable. None of those would be weird. So if I have a value of 95, it would definitely be weird for the blue. It would probably be weird for the red. It would actually not be weird for the green. And here's another visualization of the normal distribution and how within the normal you have some percentage of your data. Now, standard deviation is quite useful. It's a really useful technique for understanding the spread of data, but it is sensitive to outliers. So, for example, if you look at the first line, the standard deviation of all of these points is 0.85, and the mean is 8.65. Let's say I add in 1 outlier, a value of 1.9. The standard deviation more than triples, and the mean drops by a full point. So 1 outlier increases that standard deviation considerably to the point where we may add in a new abnormal value of 5.1. So beforehand, if we took 8.65 minus the quantity 0.85 times 3, that's about 8.65 minus about 3.4, or 2.4, excuse me, minus 2.4. So we have about 6.2. And our value of 5.1 would be anomalous in that first case. But 7.69, if you drop in a 5.1 at this point, we can't say it's weird because we had that huge single outlier. So one way that we can fix that is with a technique called MAD, median absolute deviation. This is called a robust statistic. So the idea here is that it can handle some limited number of outliers without breaking down. And what we do is we calculate the median of all the values, and then we get the median of the differences between the values and that overall median. So in other words, I take the same initial data points. The median of those data points is 8.75. Then I take the median of the differences from, say, 9.1 minus 8.75, 8.4 minus 8.75, and I get those medians of absolute values. The MAD will be the median of those, which is 0.55. So looking good so far. Then we add in that extreme outlier, 1.9. Well, that only drops the median by a relatively small amount, and it increases the MAD by a relatively small amount. So the benefit here is that if I use 3 times the MAD, I will still catch 5.1 as an outlier. It's not going to move quite as quickly to adjust to that new information. And that's really helpful in cases where I may have one dirty value, one bad value that was maybe incorrectly included, or I just had an extreme fluke that I don't necessarily want to wildly affect everything else. Next, I mentioned trend. So suppose we do have a trend, but then we have an anomalous jump. How do we separate the anomaly from the trend itself? And you can see the blue line is definitely curving upward. It's growing over time, but then we have this major spike. Well, what we can do is detrend this curve. And the idea is that we draw a line, we try to fit the trend itself, and then we flatten it. So you subtract the trend value, the trend equation, from the individual data points, and now you're left with a flat line, and you can count the vertical distance to that flat line. So fit the data with a line, track the difference for the line. And that gives you the differences and potentially the anomaly. Another thing that we want to take advantage of is that if we are using time series data, there's a concept called change point detection. This looks for abrupt shifts. So in other words, going back to driving the car, if we go from 0 to 100 in half a second, that's a very abrupt shift. That's unexpected. And we can use change point detection to track the current speed over time and pick out those cases where maybe that data was wrong or something strange has happened in here. You can take all of the things that I've talked about so far and measure them on the individual values themselves, but also on the differences between the current value and the prior value. This is especially useful with time series data because, again, we expect those not to change radically between data points. So understanding the individual values, 3 times MAD, understanding interquartile ranges, getting the trend and differences from the trend, quite useful on the initial data, but then we can also get it on the deltas, basically the first derivative of the plot. All right, we've gotten through the academic portion of the show, and now I want to talk about building anomaly detectors. And we're going to use .NET programming languages. So in my case, I'm going to use F# today. If you're not familiar with F#, no problem. It's really easy to walk through, and we'll talk through the code. If you have the desire to use a different programming language, there are some really good examples of packages in R, in Python, and even in .NET, which will help you build out an anomaly detector. So you don't have to build it from scratch. I would recommend, if you're using R, the anomalies package is really good. If you're in Python, I have not used the anomaly detection toolkit or PyOD, but in my research of them, they both seemed like they were really sound techniques. And we are going to use ml.net. If you don't have a language that has a built-in anomaly detecting package or a package you can grab, then you can check out the Azure Cognitive Services anomaly detector. So this is a web API that you can hit. So as long as you can make calls to REST APIs, you'll be able to use this anomaly detector. If you do decide that you want to build your own anomaly detection, you don't want to use a package like ml.net, check out the MathNet package or series of libraries. So you can grab these in NuGet, and they work both in C# and F# to customize statistical tests. So all of those things that I talked about, you can do with MathNet. And here are a few examples of the types of tests you can do in basically one line using mathnet.numerics. And they are quite similar to what we've talked about already. So standard deviations, median absolute deviations. You can look at MAD in one direction or the other. There may be cases where I'm not as concerned about an anomaly that is high as I am an anomaly which is low. And so you may focus on one direction. But instead of building that out by scratch, what I'd like to do instead is use the anomaly detection capabilities within ml.net. This is an actively developed library by Microsoft for machine learning within .NET. It supports both languages, F# and C#, and will give us some capabilities for this sort of analysis. So what we'd like to do is to prep this. I'm going to use Visual Studio Code. If you're more familiar with classic Visual Studio, you can easily build out an application, bring in the NuGet package that way. But I'm building out a new console application that I called Basic Anomaly Detection. I added in Microsoft.ml and Microsoft.ML.TimeSeries dataset for the machine learning portion. And I also added in xplot.plotly to visualize this. So with that, we're going to go to a demo. And what I'm going to do, I guess I'm supposed to take one of these two screens. Maybe I'll take this screen right here. And I will share desktop. Let's see if I can do the same over on this side. Nope. Okay, so I can only share on one screen. So we're going to share on this one over here. Okay. Now, hopefully everybody will be able to see Visual Studio Code, and I'm going to open up this code base here. If you can't see it, raise your hand, and maybe I'll be able to see a raised hand. But let's see if I can bump up the font size just a little bit more in case anybody has difficulty seeing this. Hopefully that doesn't go too far. What we have is an example in ml.net running an F# of some stock data. And I'm going to show you the data itself. This is from GME, GameStop. So GameStop has been in the news lately for the past several months because its stock price has been wildly varied. So let's take a look at their data. This goes back about a year ago, and the opening value was $4.25. The high was $4.76. The low was $4.16. And we're going to be most focused on this value right here, the closing value. So $4.74, $5, $5, $5. So it bounces between just a few dollars for quite a while until we get to September of 2020 when it starts hitting $10 and then it's regularly increasing. And then it just explodes in late January of 2021. That's when everybody learns about it in the news. That's where we see this peaking at about $350. But it's extremely volatile. So $340 one day, $200, $300, $200, $90, and it drops back down to as low as $40. But then it shoots back up again. And it's been kind of bouncing around the $150 to $170 range since. And we'd like to visualize this data and understand, are there any anomalies in that data? So here's how we'll do it. We're going to build out a type called price data. So this is a class in C#, and it has a few different attributes. We have a date, we've got those open, high, low, close, adjusted close, and volume. And we have these tags here that specify that this is the fourth column. So this is the first column in the data set, second column, third column, and so on. We have a type which is a price prediction. This is what we want to build out. Given a specific date, what would we have predicted the value to be? We're going to load our data from the CSV file and create an ML context. So this is what ML.NET needs in order to do its processing. Our data view is kind of what it sounds like. It is a, think of it as a way of storing the data itself in memory for .NET. So given our ML context, we want to load some data from a text file. The shape of the data is this class of price data, and it is located at gme.csv. It does have a header, and it's comma-separated values. So if you have a different setup, like semicolon separated with no headers, then you would just set those. We're going to skip past the parameters here that are set, but basically it's just detecting when we detect an anomaly and when we detect a change point. So, detect spikes. This is how I'm going to determine, is the next value an anomaly, given recent history. So we need to be at least 95% confident that this is anomalous before we'll mark it as an anomaly. And we care about anomalies on both sides, anomalies high, anomalies low. The output column name will be called prediction, and the input is close. So we're looking at that one numeric feature, and we're generating a prediction. Was this an anomaly, yes or no? And we do something similar for change points. So change points, again, were those drastic shifts on a day-to-day basis. Now, I'm going to create an anomaly model and a change point model. And for each of those, we'll fit the data given that pipeline. So for anomalies, we're going to take our data point by point. We're going to feed it in to this algorithm, and we're going to fit whether or not this comes back as anomalous. Then we're going to actually perform the transformations. So here it's this data set is going to populate. This data set, this is our process to transform. And then we're going to take our data and create a new list of price predictions given that transformation pipeline. And we'll do the same thing for change points. Now, the rest of this code is going to take that resulting data, reshape it, and allow me to plot the information. So I won't get into those details. It's basically going to give us a pretty way of visualizing it. But what I will do is build the .NET project just to make sure that everything builds successfully. Nope, I got to jump into, there we go. It'll take a moment to run through here. And fortunately, this is a fairly slight project. It doesn't have a huge amount of data, it doesn't have a huge amount of code. So building it didn't take very long. And now I'm going to kick off .NET Run, which will start the console, perform the training, and then bring up a plotted chart using F#'s xplot.plotly library. As this runs, it looks like, there we go. And here's what we end up seeing. I'm going to hide change points for the moment. And what we have is that early on, you can see there are some anomalies down here. And you may say, well, that's weird. I mean, the numbers don't look like they're changing very much. But we have prices that are like here, they're consistently going up when we would have expected ups and downs. So early on, these numbers tend to be bouncing around quite a bit. Then, let me see if I can reset my zoom. There we go. And then we have January happening, where prices just shoot all the way up to over $300. But here's what's interesting. If you look at the data set, you have all of these anomalies right here, and then it kind of stops being anomalous. And the reason it stops being anomalous is, well, we have a jump here. We had big jumps before. Basically, the variance has increased enough that we're no longer sure that that's actually weird. That may just be the norm for this data set. It was weird over here because we were consistently down below $30. We'd never hit $30 in this data set, and then we're just spiking up. So that's very weird. But now, big jumps are actually kind of normal. Okay, let's stop sharing for the moment. We're going to come back to this screen. And by the way, all that code will be available. I'll give you a link to where you can grab it. The last bit, using the Azure Cognitive Services anomaly detector. Azure Cognitive Services has an anomaly detection API. Lets you perform detection from any language that supports hitting a REST API. So not just .NET. Actually, I think it's easier to use other languages like Python or R to hit this API than .NET. But here are your steps. We're going to create a resource in Azure. We're going to save the key and endpoint, and then create an application and work with the API. So we go to the Azure Marketplace. Hopefully you're able to see this clearly enough. But on the left-hand side, we search for anomaly detector in the Marketplace, and we create one. There are two different tiers of anomaly detector. One of them is the free tier, which is what I used, and the other is the standard tier. And standard tier is going to be what you'd use in a real production environment, but just to try things out, the free tier does work well enough. It does limit you to how many calls you can make per second before you start getting errors, and the number of transactions you can have per month. Once you've created it, if you go to the keys and endpoint in resource management, you can copy the key and you can copy the endpoint. And then what I did there was I created a couple of environment variables using setX to set them for my machine. That way I can read the environment variable without having to put in the key or endpoint into my code. So that way I can check it in and nobody has access to my key or my endpoint. Now, the anomaly detector does have a full-featured demo, which I have a link to here if you'd like to try it out. But basically, if you create your own anomaly detector service in Azure, even using the free tier, you can check out different ways of visualizing some data using their page. I think it's a good way to get an intuitive feel for how their anomaly detector service works. And so I've left a link in the slides for you. But I'm going to skip that demo and talk about the API in .NET. If you're going to choose between one of these two, my recommendation is probably to use the ML.NET library. But if you have Azure Cognitive Services anomaly detection, for example, if you have a bit of code that runs in Python, a bit of code in R, a bit of code in .NET, and you want the same results for anomaly detection, then here I would use the API. So how we do that, I'm going to create a new console application again, and I'm going to call this one Azure Anomaly Detection. We'll add Microsoft.Azure.Cognitive Services.Anomaly This, unlike ML.NET, does not have a way of creating a data view. It doesn't have a ways of reading CSVs, of reading different types of data sets, and shaping them specifically for the service. So instead, we're going to have to do the shaping ourselves, and that's why I'm adding in a package called f#.data. So let's go back to the demo. We're going to come over here to this screen and try out demo number 2. Okay, close this program. We're going to drop back. I'll just build this while we're talking through it, save a few seconds, and open up this program. So the file gme.csv, this is actually a smaller file. It's only March 15th of 2021 up to April 9th. That way I don't overwhelm, because I'm using the free tier, I don't want to get any errors back. And so this is an easy way for me to limit the size of the data set and make life a little easier for me. So here's our code. We're using the anomaly detector and its models, and I'm creating what is called a CSV provider of gme.csv. This is called a type provider, and it comes from f#.data. And what happens is that it will load up gme.csv. It'll realize that we do have headers, and then we'll determine based off of the rows in here what the data types ought to be. So it's a really helpful way of creating that record type or that class under the covers without having to do all the prep work myself. So let's start from the bottom. Generally, I like to start from the bottom with F# code, and we'll say our main function. Before you run this, we do have to set anomaly detector key and anomaly detector endpoint, because you can see that the first couple things I'm doing is grabbing them. So I've already got them set up on this computer. Then I'm going to create a client, passing in that endpoint and key. Then I'm going to generate a request given the gme.csv file name. And then I'm going to detect sample async. So let's check this out. Let's start with create client. If I scroll up just a little bit here, here's create client. So this says let client be a new anomaly detector client, and I'm going to give you the key as well as the endpoint. So that one's pretty easy. The next line of code is to generate a request. This is where we start doing some real work. We're going to load gme.csv. And yeah, I do need to change its file name. I had some problems with it and decided to hard code the file name for this demo. But we're going to take this data and get all of the lines. So get all the rows in the file. Then for each line, we're going to create a new point. Point is a class that is in Azure Cognitive Services, and for anomaly detection has a date and a float of the value, so the one numeric measure. So we create a new point for each data point and make that into a list so that I can create a list that is okay for C#, which is actually an F# called a resize array. And then we create a new request. So this request is an anomaly detection request where I pass in a list and I tell it that this data is daily. I have roughly every day. Then the next line down here is to run this entire detect sample async. So what am I doing here? Well, I'm taking in my client, which is of type I anomaly detector client. I'm taking in my request, and I'm going to print that I'm detecting anomalies in the entire time series. So we'll call detect anomalies, given the client request, and we'll run this synchronously. So this is an asynchronous call that I'm going to just wait until it's finished because I don't have any other useful work to do in the meantime. So we're going to call entire detect async, which is a method on the anomaly detector service. I'll pass in my request, which is the set of data points as well as the granularity. And we're going to wait for this to finish and return the results. Once I have the results, what I get back is not the full input set plus some predictions. I actually just get back the set of predictions. So I'm going to use a function called zip. Don't think of zip as compress, like WinZip. Think of it as a zipper, where I'm joining together elements on the left-hand side and the right-hand side, except unlike a SQL join, where I join based on criteria, I'm basically just saying, first row on the left-hand side, meet the first row on the right-hand side. You're now together. Second rows, you're together. Third rows, you're together. And what that allows me to do is that I'll have my inputs, which is that request, and then I'll have my outputs, which are the predictions, and I link them back together. Then I can filter, like a where clause, given a request and a result, where the result is true. And that gives me back my anomalies. So anything that's in here is an anomaly. And what I'm looking for is how many anomalies do I have? So how big is this set? If it's 0, no anomalies. 1, I had 1 anomaly. And otherwise, I'll say this many anomalies were detected. And then for each row in anomalies, I'm going to print the date and the closing value. That was strange. So that's my code. It's only 58 lines of code long. And if I run this, what I'll see is that in the data set, we will in fact have 1 anomaly. And I believe that was on March 24th. So while that's running, let me pull up this file just to show you the data. And in this case, we can see March 23rd had a closing value of $181. March 24th was $120. 25th was $183. So it was in the 180s or so, except for this one day where it dropped $60, where it dropped 33% of its value. So our anomaly detector in Azure, given this smaller data set, picked that value up. Pop back over here so that we can wrap up. Over the course of this talk today, we've covered the concepts of anomalies, looked at some techniques for detecting them, and looked at some packages in .NET that make it easy. If you'd like to learn more, go to csmore.info/on/anomalies, And that will give you a link to slides. It'll give you a link to the code. It'll give you links to additional resources. If you have any questions at all, please do feel free to reach out to me afterwards. I have here my email address and my Twitter handle. And with that, I want to say thank you so much. If there are any questions, feel free to raise your hand or type them in chat, and I'm happy to answer them. It looks like we've got about 5 minutes for questions. For that one, for the ML.NET example, you do not need any Azure services. All you need is a laptop that can run .NET 5. All right, looks like we don't have too many questions, so thank you, everybody. Hopefully you had a great SQL day.